Now we are actually moving on to a different topic. So remember, previously we were talking about electrodynamics, and now we're moving our attention to the last topic actually for paper one, which is optical properties of matter, right? And then our first discussion is going to be around the photoelectric effect. I'm sure it's not the first time you hear of that word, and we're gonna try to define a few things that are important that are important for you to know. I'm not going to spend way too much time discussing things that are really unnecessary for you, especially at this level as you prepare for your final exam in the upcoming weeks. Okay, so now a long time ago, scientists discovered that if they shone light, so if they had a light coming, so that's the light, that's a photon of light that is coming, and then its incident is coming, it's headed towards a metal. So let's say this was my metal. They noticed that, and then we know that metals are actually very good conductors of electricity, meaning that the electrons in the metals are loosely bound so that they can move with ease. If they shone that light, something strange happened. They found that these electrons can actually be ejected from the metal, from the surface of the metal, or they could be emitted. And that whole process, that is what we define as the photoelectric effect. So photo means light. So you have that incoming light that is coming, and then the electric part of it comes from the fact that there is a sort of an electron ejection or electron emission, right? So it's not important for me to write all of that right now. So that is the photoelectric effect. So when we have some light shining on a metal, and then as a result there is an ejection of an electron. But why does the photoelectric effect happen? So this phenomenon occurs because, like I mentioned, metals are just quite good conductors. This means that these electrons are loosely bound and they can move with ease. So if you have that incoming light, it can actually eject an electron out from the surface. So it's very important to know, for you to know how to define what the photoelectric effect is. But there are a few conditions with respect to the electron ejection that we have to consider, right? So one of the things that we have to consider is that metal. So let's have different metals. Let's say we have platinum here, we have silver, and then we have gold. So all of these metals have what we call a work function. So the symbol for that work function is just given by W naught. It's measured in joules, it's energy. So so don't think it's work because it's W. That work function is measured in joules, it's energy, right? So each metal has a characteristic, a very specific work function within it. We're going to shortly define that work function, but I want you to realize that the work function of platinum will be different from the work function of silver, from the work function of, what is this, of gold. So what is this work function? This work function is actually defined as the minimum energy that an electron in the metal needs so that it could be emitted. So remember we have a photon of energy coming, and it has an energy E. Let's call that E photon. So for this, for maybe for an electron to be ejected, it will require a minimum energy, and that minimum energy, we call it the work function. So if the photon of energy has the photon of energy, the energy of the photon is less than the work function of the material, there will not be any emission, or the electron would not be emitted. So that is something important for you to know. But then, so while I'm having that conversation, I want you to first, okay, let me not wipe that. So let us define a few things. So energy of the photon E, right, can be defined using this equation hf, where we know h is what we call Planck's constant, the value of which, so h is what we call Planck's constant, and the value of which is 6,63 multiplied by 10 to the power of minus 34 joule second, right? And F is just your frequency, and it's measured in hertz. But do you know that frequency again can be related to what is it, to the wavelength through this relation over here, where the frequency is equals to c over lambda. So this is our wavelength lambda. It's measured in meters. This is the speed of light c, the value of which we know is 3 multiplied by 10 to the power of 8 to the power of 3 multiplied by 10 to the power of 8 meters per second, right? So what is that telling me in terms of that equation? Let me just wipe this. So if we have that the energy of a photon is given by hf, and that f can be written as c over lambda, this means I can just substitute this here, and then I have h is equals to c over lambda, right? So it just depends on what is it that you're given. Are you given the frequency of the photon, or are you given the wavelength? Okay, so while you're still talking about it, it's also important to define the work function. The work function is given by hf naught. So this is the frequency. So note the difference between this frequency of this incoming photon that has a potential of ejecting that electron, and this frequency here. What is this frequency? What do we call it? This frequency, we call it the threshold frequency. So this is still Planck's constant as we defined before, and this is called the threshold frequency. So what is that? We define the threshold frequency as the frequency of light needed to emit electrons from the surface of the metal. So this is the frequency that will be required, so that minimum, at least that, so that electrons can actually be ejected. The same way the work function is that minimum energy required so that electrons can be ejected. So now we can combine everything that we have just defined in one equation, where we can say, well, meaning that the energy of a photon is given by the work function. So the energy of a photon is given by the work function plus the kinetic energy. And we call that maximum kinetic energy. But where is this coming from? This is coming from the fact that in a case where the energy of a photon, where the energy of this photon is actually greater than the work function, the excess energy, so meaning it will transfer its energy to the electron, and the electron will be ejected, but we will still have excess energy. So that excess energy, remember the conservation of energy cannot be destroyed or created. It means that it can only be transferred, so it will be transferred into a motion, into kinetic energy. So that's why we have this kinetic energy over here, and that ek kinetic energy, we know that it's given by a half mv. So that's actually going to be V max squared, right? So it's just important for you to know all of these equations in terms of what is it, the photoelectric effect. And now I think what we can do is actually we can try to solve a question. Okay, so we have a question over here, and it says that ultraviolet radiation with a wavelength of 250 nanometers is incident on a silver foil, and the work function of that silver foil is 6.90, so it's 6.90 multiplied by 10 to the power of minus 9 joules, right? And then what is the maximum kinetic energy of the emitted electrons? Okay, so how do we first answer this question? So always start by a schematic, sometimes just to make sense of it. So we have a silver metal, so this is silver, and it has a work function of about 6.9 multiplied by 10 to the power of minus 19 joules. And then we have an incoming light. That incoming light photon has a wavelength of 250 nanometers, so you can write it as 250 multiplied by 10 to the power of minus 9 meters, right? And we are asked, what is the maximum kinetic energy of the emitted electron? So we know that we already defined an equation where we said the energy of a photon is equals to the work function plus EK max, the maximum kinetic energy, right? So let's see. Do we have what the E photon, the energy of the photon? Do we know the energy? No, but we are actually given the wavelength, so if we can actually calculate it. Do we know what the work function is? Correct, we know what that is because it was given to us in the equation. So there's the work function over there. So it's just a matter of taking this to the other side so that you can be left with EK max on the one side. So we can have EK max is going to be equals to E photon minus the work function. So we know that we can write the energy of the photon using HF, right? Minus the work function HF, and then we can rewrite frequency in terms of the speed of light and the wavelength minus W naught. So now we see that we actually have everything here. So we have that H is Planck's constant 6,63 multiplied by 10 to the power of minus 34. This is multiplied by 3. Okay, let me do this because I'm going to run out of space. So we just say that entire thing is just equals to 6, I don't like this marker at all. 6,60 multiplied by 10 to the power of minus 34 multiplied by 3 multiplied by 10 to the power of 8 divided by 250 multiplied by 10 to the power of minus 9. All of it minus the work function. What is our work function? It's 6.9 multiplied by 10 to the power of minus 19. And then I think if you put this in your calculator, you're supposed to come to a value of 1,06 multiplied by 10 to the power of minus 19. You can always just check these answers with me and see if they are correct, So we've actually found the maximum. So the maximum kinetic energy is equals to 1.06 multiplied by 10 to the power of minus 19 joules. All right, so that was also a straightforward question. Let us try to do take another calculation very quickly. Okay, so this is the question. It says that an ultraviolet radiation with a frequency of 1.2 multiplied by 10 to the 15 hertz is incident on a gold foil with a work function of 8.2 multiplied by 10 to the power of minus 19 joules. And then our question is quite simple. It says, would any electrons be ejected from the surface of that gold foil? So we have a gold foil right there, and then we have incoming thingy, and then the frequency of which is given there is 1.2 multiplied by 10 to the power of minus 15 hertz, and this is gold that has a work function of 8.2 multiplied by 10 to the power of minus 19 joule. So now they're asking if there are electrons here, would they be ejected? So remember our condition. For electrons to be ejected, this means that the energy of the incoming photon must actually be greater or equals to the work function. Then we will know that we will have electron ejection. If E photon is less than the work function, we would not have any electrons that are ejected. So let us actually now calculate what is it that is given to us. So we can first try to find the energy of our photon using this equation HF, right? So we know what the frequency of our photon is. It was given to us. This is just Planck's constant. It is 6,63 multiplied by 10 to the power of minus 34. And it is entire thing multiplied by 1.2 multiplied by 10 to the power of 15. And then if you put this in your calculator, I think you will come to a value of 7,96 multiplied by 10 to the power of minus 19 joules, right? Okay, so if you look at this value here and we compare it with our work function, let me do this. So we say that we can clearly see that 7,96 multiplied by 10 to the power of minus 9 joules is in actual fact lesser than 8,2 multiplied by 10 to the power of minus 19 joules. So this means that the energy of the photon incident photon is less than the work function, therefore no electrons will be ejected from the surface. So that actually brings us to the end of our discussion in terms of the photoelectric effect. You can, in the next session, we're actually going to discuss emission and absorption spectra, and then the lesson after that, we're going to do a question from a previous question paper. So keep on the lookout for those videos.